Okay, this is a brief follow-up to the first portion of the lecture covering qualitatively Newton's third law. Let me go ahead and finish up that description here with just some simple conceptual examples. Okay, now what I wrote down here on the board is basically where I was at the end of part one of this lecture on Newton's third law. I have here my two carts. Let's see, I'm calling this one here number 2 and this one here number 1. And as they are, for example, springing apart from one another, like so, then they exert the following forces. This right here, for example, is the force on 2 due to 1. Think of that as the action. This right here is the reaction. This is the force on 1 due to 2. These two forces here are referred to, by the way, as an equal and opposite reaction pair. Okay, now for simplicity, let's consider the table to be horizontal and frictionless. So then therefore the only forces that matter in this situation are the forces that I've described here. If this right here, for example, is the only force acting on number 2, just to keep things easy, then it's equal to the net force exerted on number 2 from Newton's second law. If this right here is the only force that's being exerted on number 1, once again, just to keep things simple, from Newton's second law, this is equal to the net force exerted on number 1. And then therefore, because the two forces are equal in magnitude, the MAs are equal to each other as well. Okay, and now we can use this little description here of this equal and opposite reaction pair to just qualitatively explain all sorts of different aspects of motion. So consider a situation, for example, involving a recoil, say, when you fire a weapon. So for those of you that have ever fired a gun before, undoubtedly you have felt the recoil in your hand when you did. As you fire a gun, however, which of the two objects, the bullet or the gun, has the greater acceleration? Obviously the bullet. The reason for that is because the gun has the greater mass. Now I can illustrate that here as a demonstration with my carts here very simply. Hang on a moment, I need to get a weight. I need to get one of my laboratory weights here to illustrate. So let's think of cart number 1 now, which now has more mass than cart number 2. Think of this right here as the gun, and then this right here as the bullet. Okay, now when you fire a weapon, regardless of the complexity of the mechanism, ultimately all that really happens is that the gun exerts a force on the bullet in this direction. Think of that as the action. And then therefore the reaction is that the bullet exerts the same amount of force on the gun back in the opposite direction. However, if the mass of the gun is larger than that of the bullet, this then means that the acceleration of the gun is going to be less than that of the bullet. And that then, for example, looks something like this. What you saw here in this demonstration is as follows. Think of this right here as the gun and this right here as the bullet. The mass of the gun is larger than the mass of the bullet. Therefore, the acceleration of the bullet is larger than that of the gun. So think of it as big number times small number is equal to small number times big number when talking about a situation involving a recoil. Okay, now here's another simple example of Newton's third law. What I'm going to do is face in this direction, and then with my left leg, I'm going to take a step in this direction like so. Now as I stepped in that direction, I accelerated like so. So then therefore, according to Newton's first law, a net force is present. According to Newton's second law, the net force exerted on me is in this direction, the direction that I accelerate. The question is, however, is what is actually pushing me in that direction when I take a step, for example, with my left leg like so? Now, if you're thinking to yourself, oh, it's his right leg that's pushing him in this direction. No, my right leg is not pushing on me when I accelerate in this direction. Watch the situation again, like so. As I do that, as I take a step with my left leg in that direction, what do I do with my right leg? Well, with my right leg, what I do is I exert a force on the earth in this direction. Think of that as the action. And then therefore the reaction, very simply, is that the earth pushes back on me in the opposite direction. Now, when I do accelerate in that direction, does the earth accelerate in that direction? Yes, it does. It does so in accordance with this expression right here. Think of this right here as the earth, and then this right here as me. So for the earth, you have an extremely large number for its mass, multiplied by an extremely small number. This then equals my mass multiplied by my acceleration. Does this mean, by the way, that if everybody on the Earth took a step in the same direction at the same time, would we somehow push the Earth out of its orbit around the sun? The answer to that question is no, for rather complicated reasons. However, just to keep things simple, the reason why we don't push the Earth out of its orbit is because any mechanical forces, such as this, that we could exert on the surface of the Earth by walking on it, those forces are negligible compared, for example, to the force of gravity exerted on the Earth due to the sun. It's a little bit more complicated than that as a full explanation, but for now, that's essentially the gist of it. Here are a few other conceptual examples of basically the same thing. Let's say that you have a car. The car accelerates forwards. Earlier in my lectures on Newton's first law, we went through some scenarios of what happens when a car accelerates and slows down and so on and so forth. The question is, however, is what is actually pushing the car? Now, when you press down on the accelerator of a car, all that really does is causes the wheels to rotate. So then therefore, what actually pushes the car? Well, as the wheels rotate, the rotating wheels push the Earth in this direction, that's the action, and then therefore the reaction is that the Earth pushes back on the car in the opposite direction. It's basically the same thing as what happens when I take a step like so to my left-hand side. Other examples of basically the same thing. Consider, for example, a motorboat, like the outboard motor of a motorboat. What actually pushes the boat? Well, when you operate the motor, all that happens is that the propeller rotates. But the rotating propeller pushes the water in one direction, that's the action, and then therefore the water pushes back in the opposite direction as the reaction. Same thing with a propeller on a jet engine, for example, or a propeller-driven engine for some sort of airplane. They're basically the same thing. The rotating blades of the engine push the air in one direction, and then therefore the air pushes back in the opposite direction. Couple of other examples here to finish. Consider, for example, a rocket in space. Let's say that you have a rocket in space and the rocket fires the engine. What then actually pushes the rocket? For example, there is no atmosphere, for example, in outer space, so what actually pushes the rocket? Well, think of what happened with my balloon rocket demonstration in the previous lecture. The collapsing walls of the balloon rocket push the air out the rear. This then causes a reaction where the air pushes back on the rocket. Same thing here with a rocket in space. When you fire a rocket in space, basically the rocket pushes something in one direction, the hot gas, and then therefore it pushes back in the opposite direction as the reaction. Just think of it like this. I'll use my eraser to illustrate. Think of me as the rocket, and basically what I do is I push the eraser in that direction. So if I exert a force on the eraser in that direction, it then exerts a force on me in the opposite direction like so, and I then therefore accelerate. So you operate a rocket engine by basically pushing something away from you, and it then basically pushes back on you. Speaking of my eraser, here's another conceptual example for you to wrap your head around. Okay, what I'm going to do is I'm going to tilt my phone, by the way, so it's pointed towards the door. So bear with me as I do. Okay, there we go. Okay, now let's say I'm an astronaut in space, okay? Let's say I'm doing some sort of spacewalk. Let's say that the door right here is my spacecraft, and I'm in my spacesuit and I'm outside of the door. Let's say that there is some sort of accident, like my tether broke or something like that, and I can't reach the door, and there's certainly no floor for me to stand upon. What is the only thing that I can do to ensure that I reach the door if all that I have with me is this eraser? Push it. In other words, throw it. Like that. Because if I push the eraser in that direction, that's the action, and then therefore the reaction is that the eraser pushes back. While the eraser pushes back, I then therefore accelerate in this direction. After I let go of the eraser, there is no longer a force being exerted upon me, therefore I will obey the law of inertia. I will travel at a constant velocity, a constant speed in a straight line, until I eventually reach the door. Notice how the three laws of motion begin to work together in all of these conceptual examples that I'm describing. What you will realize when I start to go through numerical quantitative examples is that it looks like I'm just concentrating solely on F equals ma as my mathematical starting point to describe various situations, but the more you examine the situations, the more you begin to realize that all three laws are actually working together. Okay, now with respect to this demonstration involving the eraser, do I really have to throw the eraser in order to reach the door? Or is just doing something like this while the eraser in my hand good enough such that I'll eventually reach the door? No, I have to throw the eraser. And the reason for that is because if I do something like this, yes, initially I'm pushing the eraser in that direction, and then therefore it pushes back, but I also stop the eraser. When I stop the eraser, I pull the eraser in this direction, and then therefore it pulls back on me in this direction. The net effect of all of this is that what is called my center of mass, which we'll get to at a later date, remains at rest relative to the door. In order for me to reach the door, I do physically have to throw the eraser, such that after I let go of it, I do travel at a constant velocity until I eventually reach the door. One last thing to conclude this portion of the lecture. Let me tilt my phone back towards my desk. Okay, let me go to the board. Okay, speaking of my eraser, I keep throwing it around. Okay, so let me back up here to one of the previous lectures with the air track demonstration. So recall the air track demonstration. Okay, just to keep things simple, let's say the air is on, so there's no friction. Okay, and then we had the air track like so. Here's our cart of mass M, string, pulley, little object off to the side, and then the cart accelerated in this direction. The little object, by the way, accelerates in this direction. And then I drew my force diagram for the forces being exerted upon the cart, and when the air is on, there are three forces. We have, first of all, the weight, mg, tension to the right-hand side. Tension, by the way, is usually abbreviated as capital T. And then I also said earlier that somehow the track pushes upwards. When I originally stated this force in the earlier lecture, I said we will come back to this and understand where this force comes from. It comes from Newton's third law. Think of it in the following way, just with my single cart. Right now there are two forces acting on that cart. We have the force of gravity straight downwards, and then we have the desk pushing upwards. Those two forces cancel each other out, and the acceleration of the cart is zero. The question is, however, is what causes that force being exerted upwards upon the cart? It comes from Newton's third law. The force of gravity causes the cart to push down on the desk. That's the action. The reaction, then, therefore, is that the desk pushes back upwards. In other words, this right here is the reaction force of the cart pushing down on the track. Therefore, the track pushes back upwards. It's a consequence of Newton's third law. I'll abbreviate Newton's third law, by the way, as N3L. You'll periodically see me write that as lectures continue. This particular force, by the way, is given a name. It's referred to as the normal force. And it's abbreviated as capital N. The word normal in mathematical lingo means perpendicular. It's perpendicular to the surface. So to summarize this air track demonstration, when the air is on, the three forces acting on the cart are the tension, the weight, and the normal force upwards. The normal force upwards cancels out with the weight vertically, but the tension, however, equals the net force in this direction, thereby giving us the acceleration of the cart. Okay, this concludes the qualitative lectures here on Newton's laws. And then what we do at this point is we start to use those laws quantitatively to begin to explain various situations throughout the remainder of this unit on dynamics.